Alright. So let me try something out with you guys here. On your paper right now, so this is position versus time, right? Mm-hmm. So everybody draw the same thing I'm drawing here. Let's say so this is me in my car. So what am I doing right now in my car? What's this axis? What's this? This is the position. Is my position changing?
No.
Okay, so let's try it again. What am I doing in my car?
Still.
Sitting at a stoplight, or I'm about to leave, or something's happened, right? I'm not moving yet, or I stopped moving, whatever. I'm not moving. Yeah, I'm texting on the side of the road. Can you take a second and continue that line? What happens when I hit my accelerator? Try to draw what would happen when I hit my accelerator. Just keep going off that line. What's going to happen? All right, and don't go too far. Give yourself some room. All right, so this is what's going to happen, right? If you hit your accelerator, you're going to do this. All right, hopefully, or it depends on your car. Your car, my old car, my first car, you go, what? Oh. Well, you remember this car. All right. So say I take my foot off my accelerator. All right. And let's. What happens if I keep going this speed for a while? If I just keep going that speed for a while? How am I going to draw my line? If I just keep going that speed, I hit a speed that I feel comfortable with. I'm right behind a cop. I'm like, you're doing the speed, so am I. So it's going to look like what? Yeah. So it's not going to do this. It's going to just follow the slope, the last slope that it was, right? So now let's say the cop in front of me stops. So I stop. Draw all that from there. Now hopefully you didn't kill me. All right, don't just go, bah! Because then I'm dead. So give me a second to stop, right? So it's a stopping distance. All right, so then we're at a dead stop because something happened in front of us in traffic. And so let's go back. So this is when I was sitting still. So velocity is 0. So the slope of this is 0. When it hit when it hit the gas, I took off. What's happening to my velocity when I hit the gas? My velocity is increasing, right? And what's the velocity? It's good. Slope of that. Now make it less calculus. It's the rate of
change of position.
Rate of change of position. So my rate of increase is increasing. Let me let that sink in for a second. How many derivatives is that? 2. I like it. Well, and so when my rate of increase is increasing, right? You guys, does that make sense when I say that? Yes. We wouldn't say that normally. You're going to go, can you make your rate of increase increase? Speed up? Yeah. And then what happens here?
It stops increasing.
Good. What stops increasing?
Your rate of change. Your velocity stops increasing.
My rate of increasing is 0. Right? The amount that my increasing position is increasing is 0. Let me let that really sink in. This is getting weird. You guys are kind of with me. So right here, what's the rate of change of position? Is it 0, positive, or negative?
Positive.
Positive. My rate of change of position, my first derivative of position is positive. My second derivative, though, is 0. Because is the rate of change itself changing? No, I love it. How do I see that? Because here it's curvy. If it's curvy, the rate of change itself has got to be changing. Maybe. Let me stop there for a second. Are we kind of with me here?
Yes.
We've talked about second derivative a little bit. We know it means acceleration, but now we're going to start talking about, well, what do the higher derivatives mean in terms of graphs, in terms of what it tells me about the graph. And then what happened here? So this is, we hit the accelerator, we hit the gas. So d squared s dt squared is positive. Oh shit. All right, we've seen this a little bit, but I'm bringing it back now. Good old second derivative. of position. I like it. Here, ds dt is what? ds dt here is... No, careful. I tricked you. It's greater than 0. That's all I can really say. I don't have a scale. My scale kind of stopped down here. It's greater than 0, but what's d squared?
0.
Equals 0. Because the amount that my slope is changing is 0. My slope isn't changing at all. If my slope is changing, that means the second derivative has to be something that's not 0. So let me see if you guys can get this last piece. Here. Right here. I have no idea what your notes look like, and I don't care. Right, right there, what's ds dt? Good, it's still greater than 0. I love it. Right? Yeah. Here it's 0. Here it's approaching 0. Hopefully I do stop before I hit the cop in front of me. That would be a bad day. Is everybody cool with the fact that that is still greater than 0? When you first hit your brake, you're not suddenly going backwards. You are still going forwards, hopefully. I don't know how strong your brakes are. Wow. That's a little too strong. But what's d squared? S dt squared. What's the second derivative? Look at it, right?
Less than
0. I like it. I like it. Because how is my slope changing? Here it's positive. Why? Because my slope is getting bigger. And of course, when something's getting bigger, that's a positive slope. But now what's my slope doing here? It's getting smaller. So the rate of change in my slope, the second derivative must be negative. So without any context at all, can you guys tell me? All right, so we got what they want from this beautiful thing. All right. So if I just give you this, screw scale, just.
That's bad traffic.
What's that? Oh yeah, true. So I don't know what this is. Could be somebody in a car. Hopefully not. I don't know what's going on. Could be. It's around here. Shit. Could be.
Is that the position?
No context at all. This is a function of some variable. I like it. Because whatever we just did for position is true for any function. Position is just a function. So whatever we just talked about is easier to talk about with position because we've been in cars. Even if we don't drive, somebody here doesn't drive, you've sat in something that moves. You've been on a bike. You've been walking on your feet. You've done this, right? You got here somehow. But any function now, what's happening here? What's happening to the slope around this curve?
It's decreasing.
My slope is decreasing. So what is the second derivative of the function? What can I say about it?
Negative.
It's negative. And look at what's really freaking cool. What shape is this? Because isn't it decreasing all the way around there? You guys with me?
Yes.
What shape is this? This is a
Parabola.
downward cup. It's down. And it's negative. When the second derivative is negative, it's a cup down is what we call it. It won't hold water. H2O. Right? What about here, of course? What's happening to the slope here? It's increasing. So this is where the second derivative is. Positive. It's cup up.
Cup up.
Gotta love that shit. Cup up, the second derivative is positive. Cup down, the second derivative is negative. That's beautiful. Thank God for that. It makes visual sense and it makes physical sense. No way. What's happening right here somewhere?
It's staying the same.
Yeah, somewhere in there, the second derivative equals 0. For just an instant, the slope isn't changing. It's getting smaller, and then it's suddenly not changing, and then it's getting bigger. So somewhere in there is a place where it's equal to 0. I like it. Let me stop there for a second. Okay, maybe. Okay. So one piece of what we're going to talk about in chapter 4, I just want to get that up there because it's based on stuff we've already done. And it really starts to get you thinking the right way about these things. Is that's what the second derivative means visually. Okay. So let's bring it back down. This is more like in later sections in 4, but I just want to start here. something that we all kind of know here. Let me draw something really weird. I like that. It's freaky looking. Now again, thankfully, let's not say that this represents motion in a car, because again, we'd all be dead after this. This is way too much acceleration.
It's a plane.
This is infinite acceleration. I don't think we could take infinite cheese, right? I didn't say infinite cheese, but I don't know. Can somebody tell me, where does the maximum happen? Yeah, and we've already talked about this kind of thing, right? We know that the derivatives tell me where, if I set it equal to 0, that's of course where a maximum or a minimum could happen. So this is a max here. And what's true about f prime of c?
It's equal to 0?
Yeah, if c is the max or the min, the derivative is going to be 0. I love it. Let me stop there for a second. But where's the min? Is there a min?
No.
Why not? Yes, there is. It's right there. Isn't that the lowest point right there?
Oh, it doesn't have it yet.
That is the lowest point. It's not an asymptotic. I would have drawn that in there. It's just one of the, what do they call it? Kink?
Yeah.
What's the book? Does the book call it a kink? It just calls it a sharp curve, whatever.
I think it's this kink.
Kink? Good. Alright, this is a kinky function. But what's true about the derivative there? Somebody remember what's true about the derivative here? Let's call this d.
Not differentiable.
Yeah, it does not exist. It's not differential. So derivative does not exist. And it makes sense to say it does not exist because derivatives are built off of limits. So it's essentially saying the limit at that point doesn't exist. The derivative here is what can you say about the slope here?
It's deep.
Big time negative, and then suddenly it's instantly big time positive. So if you drew the slope, would it be continuous? No, it's big time negative, whoops, and big time positive from your perspective. So it would not be continuous there. That's why it makes sense to call it, it does not exist. It's not differentiable at that point. But is there a minimum at that point? Yes. So where does it seem that maximums and minimums can occur? Where can they occur? Maxes and mins can occur where?
Anywhere.
No.
Well, I mean, at the highest point.
And what defines the highest point or the lowest point? There's two ways that it could be the highest or the lowest point. With the slope of 0?
And after it was positive.
No. The slope has got to be 0, or the slope has got to be does not exist, or it has to be undefined at a point. Or you could have some infinite thing we can say it's undefined. So f of x undefined or does not exist. Let's stop here for a second. Coming at it that way, is there any other way you can imagine that a function could have a maximum somewhere? All right, the only other way, it's always something, right? These are what's called, why do you think I would call it, this is a local max, and this is a local min? Because I don't know what's going to happen either. If this keeps going down, is that the absolute min? No, it's gotten lower. And if that, of course, keeps going up forever, that's not the absolute max. So we call it local max because locally it's the biggest thing. Cool? Yes. And we call this the same thing for local min. I like it. So the other way to look at this is absolute max and absolute min. Okay. I'll tell you, before we get to absolute max and min, let's do a specific concrete example of this. Oh, what you got, Jeff? I don't know, man. Let's say, let's say e to the negative x squared. Let's do that. So let me say this. Does it make sense? What points am I going to try to find? If somebody says find the maxes and mins. So the problem's going to say find the maxes and mins. Or find, they could also say this. This is also known as the relative extrema. When I say relative extrema, this is a very formal way of saying the maxes and mins. Local maxes and mins. That word relative means relative to things around you. So that's another name for local maxes and mins. How we do it? I might say that extrema. That makes sense. Extreme. Extreme values, up or down. Exactly. Calculus X cubes. So, what am I going to try to find? To find those. I got to find the derivative because I want to see where the derivative is. 0 or undefined. I like it. So we're going to give these positions a special name. The x values where these occur. They're called critical numbers. No way. So we're going to call those critical numbers. So when I say find the critical numbers for some function, that means take the derivative, set it equal to 0, and see where it's undefined. If it's equal to 0, is there definitely a max or a min there?
Yes.
No.
There's a local max in it?
Nope.
Yeah.
Here's a good one. Real quick, we still have to do this problem, but here's x cubed. What's the slope right there at 0?
0.
What's y equals x cubed? What's y prime?
3.
So y prime at 0 equals 0. So the slope is 0. Is it a max at 0?
No.
Is it a min or 0?
No.
No, it's an evil sim. I'm going to turn. No, I'm not. You guys with me? Just rested there for a second. It's like, oh man, oh shit, okay. So that could be. So definitely, wherever there is a max or a min, there has to be the slope is 0 or undefined. Period. It doesn't work the other way. Wherever there's a slope of 0 undefined does not mean it's definitely a max or a min. You guys with me? That's logic. Logic doesn't always work both ways, right? If I breathe, then I'm alive. If I'm alive, then I'm breathing. Well, no. Good stuff. All right. So this guy, like he just told me, take the derivative. To do this guy's derivative, what do I need to use? Chain rule. I love it. I love it. So it's the derivative of E is E itself.
Minus x.
Good. Derivative of the inside function is negative 2x. And then what do I want to do with that?
Equals to 0.
So this is defined in critical numbers. This is why I spent a decent little amount of time on problems involving factoring. Because when you have this problem, you know that kind of problem where it's x plus 1 to the 7th, 3x minus 1 to the 5th. And then it's beautiful to try to factor to the end. Well, because you're going to want to set it equal to 0. You want to see where the maxes and mins are, because maybe that represents your profit. And you don't want to be here. You'd rather be there. You better know how to find those places. So what do I get? What does this factor give me? X is 0? And what about this factor?
This does not exist.
Well, it's just never. What's true about exponential? E to a power. What's it look like? What does this look like? I don't know yet, but what is it?
It's a hyperbole.
In general, E looks like that, right? In this case, it's going to look a little different, but can it ever be 0?
No.
No. There you go. So that doesn't give me any answers, so don't worry about it. This is where the answers come from. All right, let me stop there. E's are going to do this to you. Anything to a power cannot equal 0 unless it's 0 to a power. When it's like, oh, duh. So if I have 3 to the who cares, can that equal 0? No, it cannot. The only thing that can equal 0 in this thing is that. If that's 0, that's 0. So what does that mean then? What's true about this?
That at 0, if there's a min or max. There might be a min.
Might be. So it's a critical number. So I like that word name, critical number, because it's somewhere where something might happen. We don't know.
Critical.
All right, well, it's critical. We'll find out. All right, so how the hell do I find out?
Graph it.
Yeah, we're going to stay away from that for right now. I don't want to graph the whole thing. And of course, at any moment, you guys could whip out your freaking TIs. And this, I'm sure, the first thing you do, and I can't blame you too much, is that. But try not to do that.
Plug it in.
Well, no, if you plug this in, plug it in where?
I think function original.
That by itself won't tell you anything. Will it tell you it's a max or a min? If you get 800, is that a max or a min? I don't know. 800 could be the minimum. I don't know. So that won't tell you enough. So here's what we're going to look at. What's important is, at a maximum, what's happening to the slope before the maximum? What's true about the slope before the max?
It's decreasing, but it's a positive.
What's true about the slope? The slope itself.
It's positive. Slope.
Positive. After the maximum, the slope is negative. That's all I got to do is look at the slope before and after. All right, so I'm going to do this. This very familiar looking thing. At 0, the slope is 0. At -1, what's the slope's value? This is always what? Positive. I love it. That's always positive. So at -1, what's this?
Positive.
Positive times positive is it's positive. At 1, what's it going to be?
Negative.
Negative. You guys with me? Where am I plugging these points?
Into the derivative.
Into the derivative, because I want to know something about the slope. You guys with me? Doesn't it make sense that if it's a max, I must have come up to it and then went down from it? That's almost too simple to believe that that's the essential part of what we're doing, but that is the essential part of what we're doing. If it's going up and then going down, must be the top of a hill. Yeah, good job. Right? If it's going down and then coming up, it must have went through a valley. It's crazy. I love it. Yes, sir.
Are there ever any situations where if the hill or the parabola is so small that it's like literally -0.1 or -0.01?
Totally. The idea of what's near, the whole idea of relative, we've already talked about this. If I control it with delta or epsilon, how small can those get? Infinitely small.
Yeah.
So it could be something that's going up and down so freaking fast, but if you make it small enough, there's a little tiny, it's like, holy shit. So it's definitely the minimum for that little tiny bit of time. So you can imagine, you could have something based off of sine or cosine where I've really zoomed in, but it's just going like crazy. And there's an infinite number of maxes, an infinite number of mins, but they are maxes and mins because right around them, it's definitely like that, right? So you guys might realize something else about what I said earlier. Let's finish this analysis. So when I plug a 1 in, I get negative times positive negative. I like it. So this is going, so underneath it, you can actually go, it's going up, it's flat, it's going down. See that? It's going up, it's flat, it's going down. So this is the location of a maximum. So the max is where? 0, comma what?
2. Or what is that?
That's a Z for 0.
Yeah, 0, 0.
No. What's the point? Where's the point? What function do I use now? To figure out what the point is. The original function, exactly. Don't plug 0 in here. You're going to get 0, of course. We already knew it's 0 at 0. That's why it was a critical number. If I want to know what the point is now, what's the actual maximum value, you got to plug it back into the original function. I don't know if you guys remember I was saying, when we take all these derivatives, and we're going to start taking second derivatives also, you got to know which one to plug it into, depending on what you're trying to figure out right then. Why did I plug it in here for this? Because I need to know what the slope was doing. Why am I going to plug it in there? Because now I need to know where the hell the function is. What's the point? So when I plug a 0 in, what do I get?
1.
1. I like it. So this function has a local max at 0, 1. Does it have any local mins?
No.
If it did have a local min, we should have found
A critical point.
another critical number to go with that. If it has maxes and mins, they must be critical numbers. But not every critical number has to be a max and a min, or a min. That's with me. Logic doesn't work both ways. All right. So here, right off of that, I think it's perfect. You guys do this. This is a very, very to the point little handout. You guys are like, yeah, we'll see. With that. Bless you.
Thank you.